We've been talking about the dimensionality of physical properties of water. Now I'd like to move on to the dimensionality of some chemical properties of water and how we can use those in a way to estimate some of the physical properties of water they're related to. In particular, I want to review some of the concepts of solutions. The idea that you can dissolve solids into a liquid and talk about how much of that solids and liquid are part of that solution. And I want to talk about an example of how to apply that to estimate some unknown volume of water. So say we have water in a bucket as before, and we want to know something about how much volume of water is there, and we don't have the means to get the volume with a graduated cylinder or something like that. But what we do have is we have some salt and we have an electrical conductivity meter. I'm going to talk about how we could get to an estimate of a volume with those devices based on knowing something about solutions. So just some of the language of solutions. You're going to have a solute, or the stuff that is dissolved. In this case, we want to use sodium chloride. We'll talk about sodium chloride. It's a really common hydrologic tracer because it tends to behave conservatively. The sodium and the chloride don't react with things once they're dissolved in the water. In our case, the solvent is water. And sodium and chloride tend to completely dissociate. The ions tend to completely dissociate in water because water is a polar molecule, and water is very good at surrounding things with a charge based on the charged ends of the water molecule. This polar characteristic of the water molecule makes it what we call a nearly universal solvent. So other than some of the organic molecules that don't have a charge on them, water is very good at dissolving things. And sodium chloride, for example, is extremely soluble in water. It's remarkable just how much mass of sodium and chloride you can get dissolved in water. So the way we quantify concentrations is with a variable that we might call C of a solution here, or the concentration of a solution. And dimensionally speaking, we can derive what the dimensions of that concentration would be from how we do the calculation with other variables. So one of the ways to characterize a concentration of a solution is to take the mass of the solute and divide that by the volume of the total solution it's dissolved in. So dimensionally speaking, we've got the fundamental dimensions of mass in the numerator, and we've got a volume in the denominator, which we've talked about as being a length cubed. So we have a mass per length cubed here for our dimensions of a concentration. Now there are other dimensions that you can use for concentration, but this is the one we're going to focus on. Now, when we dissolve things into water, it tends to change some of the physical properties of the water. And one of the properties that putting salt into water will change is electrical conductivity. The electrical conductivity of water tends to be very sensitive to how much chloride is dissolved in the water. So that gives us a property of the water that we can measure to make an inference of how much salt might be dissolved in the water. And using that measurement of this solution, the concentration of the solution, might give us a way to estimate the volume of a solution if we know how much mass of the solute we put into that solution. So that's the idea that we want to pursue here. Before I get to that though, I want to talk a little bit about being careful with dimensions. They don't tell you everything. You need to know something about the mass of what and the volume of what to make sense of dimensions. Also, dimensions, there might be several different dimensions for the same property. For example, we use a lot of different dimensions to talk about the concentration of solutions. Concentration can be provided in molarity, and that's moles per volume. Now moles is a count. It's just a particular number based on Avogadro's number of molecules. So it's actually a dimensionless number. Molarity is one of those variables that has units but does not have dimensions. So molarity is just per volume. The dimensionality of molarity is per volume. Molality is per mass. Same thing, moles per mass. Percent by volume is a measure of concentration that you might see if you're looking at a can of beer or something like that. Usually percent by volume is how alcohol percentages are provided on alcoholic beverages. So concentrations can have a lot of different dimensions or no dimensions. So the dimensions aren't telling you everything. You have to know a mass of what, volume of what. Were you talking about the solute or are you talking about the solvent? Also, mass per volume is not always a concentration. Just because you know the dimensions doesn't mean you know what it is. If you can think of what mass per volume might also be, if you have a mass of something related to its volume, that's also the dimensions of density. So you have to, again, you have to know mass of what, volume of what to make sense of these dimensions. Context is everything. You can't just work from those letters alone to understand what dimensions are telling you. So I just wanted to add a note of caution there to make sure you're being a little bit careful in understanding the context of mass and volume before you interpret these dimensions. So as I mentioned, adding solutes, especially dissolved solids, to water tends to have a strong effect on the electrical conductivity of the water. Now here's one case where we're not going to get into the dimensionality of electrical conductivity because it gets complex into electrical properties of physics, and that's just not somewhere that we want to go in the scope of this class. But the units for conductivity that we measure are in typically something like microsiemens per centimeter. A Siemen is the same thing as the inverse of an ohm, or what's sometimes called a mho. So it's the inverse, the conductance is the inverse of resistance, and a microsiemen is a unit of conductance, and per centimeter tells you something about it being normalized to a particular geometry of what you're measuring the conductance of. Now this conductivity, this electrical conductivity that we can measure, will vary with the dissolved solids in the water, but unfortunately it also varies with temperature. Fortunately, the variation of conductivity with temperature is a pretty well-known relationship. So what we tend to do is normalize for temperature. So we have a temperature-corrected conductivity, or it's sometimes called the specific conductivity or specific conductance. And that means you are specific to the temperature that water is at. So the idea is you say, what would the conductivity of the water be if the water were at 25 degrees Celsius? What this does is it normalizes the variation in the conductivity to no longer be a function of the temperature. We've corrected for the effects of temperature. So the only variation we should have left in conductivity and a temperature-corrected conductivity should be due to the dissolved solids in the water. This is really important when you're reading a conductivity instrument. You want to make sure you're looking at the specific conductivity if you're trying to understand the concentration of a solid from that number, and not just the raw conductivity that is not temperature corrected. And we'll point that out in future labs when we start looking at these devices for measuring these properties. So this relationship between electrical conductivity and concentration gives us a way to measure the solute concentration with a fairly simple device that measures electrical conductivity. In our case, we can make a reasonable assumption that an increase of 1 milligram per liter of sodium chloride is going to increase the specific conductivity, the temperature-corrected conductivity, by 2 microsiemens per centimeter. Now I use that circa there, that's just Latin for saying about 2 microsiemens per centimeter. This does vary a little bit, but unless you're talking about really strange water chemistry in fresh waters, this is the kind of relationship that you're dealing with. Now what's kind of cool about the abstractness of dimensions is the units don't matter. And we know that 2 microsiemen per centimeter change is consistently tied to 1 milligrams per liter, no matter what conductivity we're talking about in the ranges of fresh waters that we're dealing with. That means we can treat microsiemens per centimeter dimensionally just like a concentration. We can say those two are just like each other, and therefore we can use that approximate equality to make a conversion from a measurement of conductivity to a measurement of concentration, just like we do a unit conversion using the unit factor method. And I will get to an example of that in just a minute. So even though those are very different units and on the surface appear to be very different dimensions, because those two are consistently related to each other, we can dimensionally treat a conductivity unit as if it were a concentration. I'll show you how that works in a minute.